Okay, class. So you just finished the section on continuous distributions. These next three chapters are going to be all about the distribution of x bar, the mean of x. All right, so in the previous chapters, you covered simple probability, you covered discrete distributions, which included the uniform, the binomial, the Poisson, and the hypergeometric. You also covered continuous distributions, which also includes the uniform, the exponential distribution for time to an event, and the normal distribution. If you've had trouble with the normal distribution, you really need to go back and reread that section because the next three chapters are all about the normal distribution. Get good at using your z-tables. Get good at using the norm inverse function and the norm distribution function in Excel. You're going to be using those quite a bit in these next three chapters. So why do we care about the distribution of x bar instead of the distribution of x? All right. So in the previous chapters, we would assume that the random variable x was normally distributed, and it had a mean of mu and a variance of sigma squared. We assume that. However, we don't really know if the distribution of x is really normal in reality. We don't know if it's exponential or if it's uniform. We don't really know. We're just grabbing a sample and we're hoping it fits into that particular distribution. In fact, x could look really different from a normal distribution. And in one of my other videos, you actually do see how I could take an x that looks completely goofy, right? It has all different types of spikes and hills, but it will converge to a normal distribution if we look at only x bar. And so, how can we continue doing statistics if we don't really know the distribution of the random variable? Enters the central limit theorem. The central limit theorem says basically the following. Regardless of the underlying distribution of x, the distribution of the mean of x is approximately normal as the sample size becomes large. So what this theorem means is we can still use the normal distribution to do statistical testing as long as we talk about the mean of the random variable and not the actual random variable. So these next three chapters are going to be all about the mean of x, all about the sample mean of x. And the way it works out is when we apply the central limit theorem, we still get the same population mean that we had before, right? So we still get this mu. But now we have this new function here for the variance of x bar. And notice something peculiar about this function of the variance of the x bar. As n gets really, really big, right? So as n goes to infinity, the variance goes to 0. Right? Your variance is going to get smaller and smaller and smaller and smaller. This is actually a good thing. It's showing that x bar is a consistent estimator of our population mean. In other words, this means that the sample mean converges to the true mean as the sample size gets large. The way to think about this logically is that if your sample size is the size of the population, then your sample mean should equal your population mean, all right? We're going to be using this fact, the fact that regardless of the way that x itself looks like, the mean of x is going to look approximately normal to do more of our testing. Now you might be wondering, well, how do we get this function to begin with? Okay, that's what the next slide is going to be about. Let's start with our underlying x actually being normal. And this doesn't have to be true, but for simplicity of the math, it works out a little bit nicer. So let's say that our original x has still a mean of mu, and it still has a variance of sigma squared, all right? We're going to use this little variance function, and this variance function simply says that tell me what the variance is of the random variable that's inside the parentheses. In our case, we're saying tell me what the variance is of x. Well, we already know it's sigma squared, so we get it's equal to sigma squared. Well, what if we multiply x by a constant a? Now remember, a constant doesn't change, right? It's just one value. It's either 2, 3, 4, what have you. It's one value. If we multiply our random variable x by a, then the new variance is going to be a squared times the variance of x, which is sigma squared. Well, what if we let a be equal to 1 over n? All right, so 1 over n being the sample size. Then our variance of x is going to be sigma squared divided by n squared. Hopefully you see where we're going with this, right? Well, now, what if we're looking at the variance of x bar? Well, what I'm going to do now is plug in what the formula for x bar is, what the formula for the mean is, right? Remember, we sum up all of our values and we divide by the sample size. So that is the formula for x bar. 1 over n is just a constant. And since it's just a constant, it can come out front as a constant squared. So 1 over n squared, right? Now we're concerned with the variance of the sum of the x's. Here, it might get a little bit more confusing. You might say, well, how can I use this function over a sum value? Remember, one of our assumptions of a random sample is that each one of the x's are chosen randomly. And if each one of the x's are chosen randomly, then there is no covariance between x1 or x2, right? They don't talk to one another. So because of that, we can actually push this variance operator inside of the sum. And we can rewrite it as 1 over n squared, the sum of the variance of x. But we already know what the variance of x is, right? We got that from back here. We know that the variance of x is just equal to sigma squared. So we can replace this part with sigma squared, and now what we're doing is we're summing up sigma squared n times. In other words, we're doing sigma squared plus sigma squared plus sigma squared plus sigma squared all the way up to n. And that's going to give us n times sigma squared divided by n squared. All we're going to do is cancel out one of the n's here, and we're going to get sigma squared divided by n, which is exactly what we found on the previous slide, right? That's exactly the amount we need. So now moving forward, we're going to apply all the same rules that we had in the previous section when it comes to confidence intervals, when it comes to probability testing, except now we're going to be using this as our variance term. All right. More appropriately, we're going to be using the square root of this as our standard deviation. You'll notice there'll be a slight change in vocabulary. Whenever we talk about the standard error, we're really talking about the standard deviation of x bar. And whenever we talk about the standard deviation, we're really talking about the standard deviation of just x. Hopefully you found this video useful and as a nice guide into these next 3 chapters.